In today's lesson, I'm going to talk to you about entropy, which is a new concept for most of you, and the second law of thermodynamics. So thus far, we have talked a little bit about enthalpy and how that affects whether a reaction is spontaneous or non-spontaneous. So we just want to review again, just quickly, what spontaneous means. And on one note here, your textbook uses the word spontaneous, but that language is not used on the AP exam. On the AP exam, they will use thermodynamically favorable, which means that it is favored in terms of the entropy and the enthalpy. So just a quick note there. But a spontaneous process, or one that's thermodynamically favorable, is one that will continue to happen without any outside intervention. So we've already talked about many of these types of processes. So for example, if you have a cup of hot coffee, it will spontaneously cool to room temperature and then it will stop. It will not spontaneously freeze, but it will spontaneously, and it wouldn't spontaneously warm back up, but you can get a sense for what kinds of things are spontaneous or non-spontaneous just in your everyday life. Right, so this sentence here, which is in your notes, should say, does non-spontaneous mean impossible? So just because something is not spontaneous doesn't mean that it can't happen. It just means that outside energy needs to be put in for it to happen. Okay, and it's important to note that something that's spontaneous doesn't necessarily happen quickly. So spontaneous just tells us whether it's favorable to happen thermodynamically. It may be an incredibly slow process. So for example, I talked about in the last a couple lessons ago that graphite is more stable than diamond. So thermodynamically speaking, graphite could convert to diamond, but that doesn't happen because it would happen on such a small, slow time scale that we wouldn't ever see it happen in our lifetime. So I just want to reiterate that spontaneous doesn't necessarily mean that it's going to happen quickly. All right, so given that we learned previously with the stuff in chapter 6 that a negative heat of reaction is generally a thermodynamically favored process, but we know that sometimes things that are that have a positive heat of reaction, that are endothermic, happen spontaneously. So for example, melting is a process that requires the bonds in, or the interactions in the solid, to break down so that it becomes a liquid. So that is an endothermic process, and yet it happens spontaneously at room temperature. All right, a cold pack. So usually we don't think of things spontaneously getting cold, colder than room temperature. But if you've ever had an injury on the sports field, you've probably encountered cold packs. So you crack them open and then say they suddenly get cold spontaneously. So that is definitely an endothermic process because we're feeling all of that, that cool temperature when it happens. And yet it still happens spontaneously. And also, if we have a hot skillet, or like the hot coffee that I talked about just a second ago, that will spontaneously cool down if it's sitting at room temperature. So these are all endothermic processes that are also spontaneous. So there must be something else at play. And that something else is entropy. So formally, the definition of entropy is a thermodynamic function that increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. So that's a lot of words, which basically is analogous to randomness. So entropy is a measure of how many different ways we can arrange the system and get an energetically equivalent outcome. So we're going to do a lot of examples of this because this is a sort of an abstract concept to grasp. So what you need to know is that energy prefers to be as spread out as it can be. That's just naturally what happens. And it is favored for energy to be spread over many particles or a larger volume, or both, rather than being concentrated in just a few particles or in a small volume. So let's take a look at some processes that you've encountered in your everyday life and talk about whether that entropy change for the system would be positive or negative. So a can of soda over time loses fizz. So the fizz would be our system, and if it's in the soda, we have gas molecules that are confined to the can, right? They are dissolved in the liquid, which is what gives us that fizz, that carbonation. So as the soda loses its fizz, those gas molecules are escaping the solution and being released into the air. So since I just told you here that particles or that energy would prefer to be spread over a larger volume, the gas molecules, once they're released out of the soda, are going to take up a lot more volume than the can of soda did to begin with. So this would be a case where the entropy of the system increases. It's positive. All right, the second one is a protein precipitates out of solution, creating a crystal. So if the protein is in a crystal form down at the bottom, it's in a very small volume and very compact and very close together. Whereas if it was dissolved in the solution, it's going to be spread all over the place, and so that would be higher entropy. So if we're going from in solution to in a crystal, then that would be a negative change in entropy. Right, the third one is solid carbon dioxide sublimes. So the CO2 molecules are going to be very close together and very ordered when they're in the solid form. And if it sublimes, now they're in the gaseous form. And so that would be an increase in entropy or a positive change. The fourth is water condenses from a gas to a liquid. So that happens sometimes on a hot summer day. If you have a cold beverage, you will get gaseous water from the air will condense on the side of your glass in the liquid form. So again, spontaneous process, but this would be a case where the change in entropy is going to be negative because the gas molecules are very spread apart, and then when we put them in the liquid form, they're very close together and don't have near as much freedom to move around. So the second law of thermodynamics relates to this, and the second law tells us that for any spontaneous process, the entropy of the universe increases. Okay, so in order for the entropy of the universe to increase, if we have a process where the entropy change in the system is negative, then that must mean that there's a big enough entropy change in the surroundings that will still allow for an increase in entropy of the universe. Right, now we're just going to go through some chemical examples. So here are some standard entropy values for different substances. So the first question is, what happens to entropy as a substance changes phase and why? So in this table here, we have some of the same substances in multiple cases, but in different phases. So liquid water has an entropy of 69.91, whereas in the gaseous state, it's 188, so much bigger. Okay, same thing for carbon. Graphite, it's 5.74. And carbon in the gaseous state is 158, much, much bigger. And this process, or this trend continues throughout the table. So carbon tetrachloride in the liquid state has a smaller entropy value than carbon tetrachloride in the gaseous phase. So as we go from solid to liquid to gas, the entropy increases. So the entropy of a solid is going to be smallest, and the entropy of a gas is going to be the biggest. Right? The second is, what happens to entropy as a molecule becomes larger or more complex? And if we take a look here, if we have just plain old carbon in the gaseous state, that has an entropy of 158. If we attach 4 hydrogens to it, now it has an entropy of 186. If we add another carbon and 3 hydrogens to that, then we're up to 229. Add a third carbon, up to 269. Add a fourth, and up to 310. So the more complex your molecule gets, the higher the entropy becomes. Another factor that we can look at is the entropy as the force of attraction changes, and this is in an ionic lattice here. So one way to measure the force of attraction is the melting point. So the higher the melting point is, that means the more you have to heat it up to break those attractions. So high melting point means high force of attraction. And what we see here is hopefully what you would expect, which is that ions that don't have a strong attractive force, so have a lower melting point, have a higher entropy than ones that have a very strong attractive force. So the stronger they are held together, the lower the entropy is. All right. For number 4, what happens to the entropy when a pure liquid or solid dissolves in a solvent? So if we dissolve it in a solvent, so if we look at the liquid versus the aqueous, once it's dissolved, it's going to have more space to move around, and so that increases the entropy. So entropy also favors mixing, so that's another way to think of this particular. Now, finally, let's take a look at what happens if we dissolve a gas in a liquid. So this is similar to the soda that I talked about in the beginning. So a gas has lots and lots of space to move around and lots of different ways to spread its energy out. Whereas if we dissolve it in a liquid, then it's confined to the volume of that liquid. And we know gases like to spread out. So dissolving a gas in a solution actually decreases the entropy because we're now confining it to a smaller space, a smaller volume. So now let's get into why it is that we can have, or what the relationship is between heat transfer, which is the enthalpy we've been talking about, and changes in entropy. So if entropy decreases when we go from a liquid to a solid, which is what it does, then why would water spontaneously freeze if it's below 0 degrees Celsius? Why, when you put it in your freezer, does it turn into a solid if that's an endothermic process? And the answer is relates back to the second law of thermodynamics, which I already told you, which is that the entropy of the universe is always increasing. So if the entropy of the universe is going to be the sum of what's happening in your system and what's happening in your surroundings, then the change in heat in your system is also changing the heat in your surroundings. And so that actually influences the entropy. So when a system releases heat, that increases the entropy of the surroundings because that energy in the form of heat is now being dispersed throughout the surroundings and has more places to be. So that's an increase in entropy. So in order for this to be true, what we know is that if we have an exothermic process, this is one that releases heat into the surroundings, that means that that must increase the entropy of the surroundings. And an endothermic process, which is one where we use up heat from the surroundings, that process would decrease the entropy of the surroundings. So let's look at an example and how we would measure this quantitatively. So freezing of water is not always spontaneous. Delta S of your surroundings is temperature dependent. So the greater the temperature, the smaller the increase in entropy of the surroundings. So if your surroundings already have a good bit of thermal energy, then increasing the temperature a little bit doesn't actually make very much difference. But if your surroundings are very cold, like in your freezer, when you increase the entropy when you increase the heat in the surroundings, you increase the entropy more than you would if the temperature were higher. And this relationship is characterized by the equation delta S of the surroundings is equal to minus delta H of the system over T. All right, so if we have a negative delta H, that's a positive delta S of the surroundings, and if we have a positive delta H, that's a negative delta S for the surroundings. Now let's do an example and do all the calculations we need to do to figure out whether this reaction is going to be spontaneous or non-spontaneous at room temperature. So we have a combustion of propane gas, which is C3H8, and the delta H of the reaction is negative 2,044 kilojoules. All right, so if we want to first calculate the entropy change in the surroundings associated with the reaction, we use delta S of the surroundings equals minus delta H of a reaction over T. And in this equation, T must be in Kelvin. Right, so that's going to be a positive 2044, because a negative of a negative, divided by 298 Kelvin, because remember we want to do 25 plus 273. That gives us a positive 6.86 kilojoules per degree Kelvin. Right? Now, let's determine the sign of the entropy change for the system. So if we take a look at the system, there's not much difference in the complexity of the molecules on the left and the right, but they're all gases, so the biggest change is going to be how many moles of gas is going to be on each side. So on the left, we have 1 mole of propane and 5 moles of O2, so that's 6 moles of gas altogether. And on the right, we have 3 moles of CO2 and 4 moles of water. So that makes 7 total. So we're increasing the number of moles of gas in our equation, which means that the entropy for our system is going to be positive. So given that the change in entropy for the system is positive and the change of entropy for the surroundings is positive, that means the change in entropy for the universe will also be positive, and we have a spontaneous reaction.